Welcome to the Professor's DuBois channel. This is Professor Victoria, and I'm here to teach you about molecular shapes. I'm going to be using a simulation today from an outfit called PHET of Colorado. It's a fantastic organization who has put together a lot of simulations for the advancement of science and math. So thank you so much, PHET of Colorado. And here we go. So we're going to go through several different types of molecular shapes, and they are based on something we call the Vesper Theory. It's really VSEPR. It's the valence shell electron pair repulsion theory. It's a little bit simplistic and perhaps some might say out of date, but it goes a long way to explain simple molecular shapes, and that's really what we're trying to get down to. So in this Vesper theory, the electron densities around a central atom are pushed apart as far as they can. They're repelled, right? So these electrons are negatively charged, so they're repelling each other. So in this theory that these electron densities will be as far apart as possible. So in this molecule that I have here on the screen, we have two bonded atoms, and they are, of course, as far apart as possible is 180 degrees, and they make a linear molecule. So I just want to show you what's on the screen here. So we have something called an electron pair geometry and a molecular geometry. And the electron pair geometry takes into account everything that's around something called a central atom. So a central atom I'm showing here. Molecules can have several central atoms, but we're just going to concentrate on single central atom molecules, very simple, so that you can learn your geometries and your bond angles. So the central atom is what you base your geometry around. So it's linear with respect to this central atom. And these outside atoms, the bonded atoms, are called terminal atoms. So they are bonded to the central atom, but nothing else. We have the bond angle, that's pretty obvious. Lone pair, so if we have a lone pair on our central atom, it will look like this. So if you're doing your Lewis structures, you know you have your bonds and your Lewis pair or your lone pairs, which are comprised of the two electrons occupying that space. And that space we're going to call a domain. So bonded atoms plus lone pairs are your total number of domains. And these are the quote-unquote the things that are around the central atom that are repelling each other and getting as far apart as they can. So if I go back to linear, so we have linear, that's with two domains around the central atom. You might hear this also as a steric number, so a steric number of 2. The electron pair geometry takes into account the number of domains that are repelling each other. The molecular geometry, on the other hand, is what the molecule looks like. So we're going to talk about how, when these are different, as we go through the different types and the different shapes. So when we have 3 bonded atoms, we have what's called a trigonal planar geometry. So there are 3 domains as far apart as possible, and the bond angle is 120 degrees. So I'm going to manipulate this around a little bit so you can see how this is in a plane. So there are 3 things in a plane, that's why we call it trigonal planar. When we don't have any lone pairs, the electron pair geometry will be the same as the molecular geometry. And that's for any of the shapes, for any of the number of domains. If there's no lone pairs, these two will be the same. So I'm just going to take off this bond angle just so we can see this a little bit different. If one of these is replaced by a lone pair, we still have a trigonal planar electron pair geometry, but now our molecular geometry is just bent. So it's bent 120. If I don't show the lone pair, you can see how the molecular shape is still bent. We can't see that lone pair, but that's why these two are different. The molecule actually looks a little different. So I'll go back and be able to see that. So what if we'll take this away, and now I'll go to 4. Oops, we'll have 4 different bonded atoms here. When we have 4 domains, the electron pair geometry is a tetrahedral, and all of these are 109 degrees apart. It doesn't matter what way we move this, it's always the same. Looks like a tetrahedral. So this molecule doesn't have a top and a bottom, it always looks the same. If there's no lone pairs, these are the molecular geometry is the same as the electron pair geometry. But if we replace one with a lone pair, now these are different. The electron pair geometry is still tetrahedral because we still have 4 domains, but our molecular shape is now a trigonal pyramidal. So there's 3 things on the bottom here, and it looks like a pyramid. So if I don't show the lone pair, there's a trigonal pyramidal. And our bond angles are still 109.5. If we have 2 lone pairs, I'm going to show them. Now we have 2 lone pairs and 2 bonded angles, or 2 bonded atoms. The electron pair geometry is still a tetrahedral, so our bond angles are still 109.5, but you can see that the molecule, there's 2 of these domains made up of lone pairs that we really can't see. So now the molecule is, again, it's bent, but it's bent 109.5, and that's really important distinction, because if it's 120, then it came from a trigonal planar, 3 domains. But if it's 109.5, it came from 4 domains, 2 lone pairs, 2 atoms. That's an important distinction. Okay, so let's remove these lone pairs and add 1, 2, 3, 4, 5 atoms. When we have 5 bonded atoms, or five domains, and they're all bonded atoms, we have the same geometry for each. The electron pair geometry is now called a Trigonal Bi-Pyramidal. So it's it's like a 3-sided pyramid on both the top and the bottom. So that's where the that's two pyramids of 3. If all of them are atoms, then these 2 are the same. I want to point out there are a difference between these atoms. We have equatorial positions, so I'm spinning this kind of like the Earth, and then the equator. Oh, it just moved on me a little bit. Nope, it didn't. So these are axial positions, as if the axis of the Earth, and these are the equator, the equatorial positions. Notice how the equatorial positions are in a trigonal planar arrangement. So they are 120 degrees between them. So around the equatorial, these are 120, and then we have 90 between them. The axial and the equatorial. There we go. There. Now you can see the trigonal planar, 120, and then we have an atom coming out of the screen and going back into the screen. If one of these atoms is a lone pair, the lone pair will occupy an equatorial position first. That's really important. And a trigonal bipyramidal with 1 lone pair is a seesaw. So I don't know if you can see that, but it kind of looks like a seesaw. Here's where the kids can sit. It's hard to show you. There we go. There it is, seesaw, up and down. If one of these atoms is replaced with another lone pair, so we have 2 lone pairs, again it occupies the equatorial positions, and we're left with still a trigonal bipyramidal because we have 5 domains, but now the molecule looks like a T. It's a T shape. Still the same bond angles. If another lone pair is added, all 3 of the equatorial positions are now occupied by lone pairs, and we have a linear molecule. So back to linear. And this bond angle is 180. Okay, so if we remove these and go back, there are more, but the last that you are going to be responsible for is the last electron pair geometry is octahedral, and that's where we have 6 domains, and the 6 domains all occupy, they're all 90 degrees from each other. It doesn't matter which direction we put this, it always looks the same. Kind of looks like a jack, bouncing ball game jack. All right, so we have all of these are 90 degrees apart, and we call it an octahedral. If there's no lone pairs, then these are the same. If we replace one with a lone pair, the first one doesn't matter which location it occupies, which domain location. And we're left with a square pyramidal molecular geometry. So this is occupied by a lone pair, so if we don't see it, this is what it looks like. So I put this on top, square on the bottom, and then a pyramid. if one lone pair, another lone pair is added, it will occupy the space opposite the first one. And that's really important because the electron pair geometry of octahedral with two lone pairs is a square planar. So you can see the square and it's all in a plane. See that? Square planar. Those are the geometries that you will be responsible for. I want to point out one more thing. It doesn't matter if the bonds are single or double or triple as far as domains go. So if we have two single bonds and a double bond, it's really still three domains. You can notice how we still have a trigonal planar electron pair geometry and molecular geometry, and it's still the same bond angles here. So when you're counting domains, don't count bonds, count number of atoms that are bonded to the central atom and lone pairs. Okay? Count a double bond as one. That's really important. So you need to know the name of the electron pair geometry, the molecular geometry, and the bond angles for up to 6 domains with the different lone pair, numbers of lone pair options. And I would recommend going back to this simulation and practicing. You can go to something called real molecules as well as the model. And it's very interesting, very helpful, I think, to learning these shapes. So thanks for watching. Please give the video a thumbs up and subscribe for more videos from the Professor's DuBois.